Hello everyone. Today I will discuss about nerve agents. What are nerve agents? How to detect this nerve agent? What are its side effects? These are my contents. First introduction, synthesis, results and discussion, and last conclusion. Introduction. So what are nerve agents? Nerve agents are highly toxic and most hazardous chemical compound. They have a harmful effect on the health of living organisms including humans. These agents are considered weapons of mass destruction and have been developed primarily for military purposes. They are extremely hazardous and pose a significant threat to civilian population. Nerve agents belong to class of organophosphorus compound, which are characterized by their ability to inhibit the activity of the enzyme acetylcholinesterase. Acetylcholinesterase is responsible for breaking down the neurotransmitter acetylcholine, which regulate the nerve signals in the nervous system. By inhibiting this enzyme, nerve agent cause a dangerous accumulation of acetylcholine at nerve endings, leading to overstimulation of the nervous system. Nerve agents are divided into two series, that is G series and V series nerve agent. Here I will discuss about only G series nerve agent. The German scientist Gerhard Schroeder first discovered this G series nerve agent in 1936, and first ever G series nerve agent discovered was tabun, and then serine, and then so on. Nerve agent attacks. Serine is considered as one of the most deadliest nerve agents and has been used in several incidents. And some notable incidents are Tokyo subway attack. In 1995, serine gas was released in Tokyo metro, resulted in 12 people were died and thousands of people were severely injured in this incident. In 2013, a large-scale sarin gas attack occurred, resulted in hundreds of civilian deaths in Syria during Syrian civil war. In 2017, the V-series nerve agent was used in the assassination of Kim Jong-nam, the half-brother of North Korean leader Kim Jong-un. Poisoning by nerve agent may lead to following symptoms such as eye pain, constriction of pupil leads to blurred vision, cough, weakness, headache, low or high blood pressure, or ultimately death by asphyxiation or cardiac arrest. Since nerve agents are highly toxic, it is not possible to use this real nerve agent. So nerve agent mimics are used, such as diethylchlorophosphate and diethylcyanophosphate, in short DCP and DCNP, due to its low toxicity and similar activity towards tabun and serine respectively. The structure of DCP and DCNP are as follows. Methods developed. So far, several methods have been developed, and such as mass spectrometry, electrochemistry, surface acoustic wave sensors, etc. But these methods suffer limitation due to slow response, limited selectivity, and low sensitivity. An alternative method known as fluorescent chemosensor gained attention in recent years due to high selectivity, fast response, and high sensitivity. Now the main point in this are we have synthesized a compound known as SDO. Actually we have named this compound as SDO, prepared by a simple condensation reaction between 4-aminothelimide and N,N-dimethyl-cinnamaldehyde using methanol as a solvent. The reaction is carried out at room temperature for 4 hours, resulted in the probe called SDO. The structure of the SDO is confirmed by proton NMR, carbon 13 NMR, and FT-IR spectrum. In UV visible absorption studies, the absorption spectral studies of SDO were performed in DMSO water solution 20% with addition of different analyte. The addition of DCP to the SDO solution resulted a new peak appears at 390 nanometer, which shifted from original peak at 399 nanometer by 9 nanometer. Actually the peak shift from 399 nanometer to 390 nanometer. The shift is about 9 nanometer. Similarly, the addition of DCNP to the SDO solution resulted a new peak appears at 399 nanometer, which shift from appears at 388 nanometer. Upon addition of DCNP to the SDO solution resulted a new peak appears at 388 nanometer, which shift from original peak at 399 nanometer. That is, the shift is about 11 nanometer. In both the cases, the color of the SDO changes from yellow to colorless, which indicates the selectivity of both NARP agent towards SDO. Fluorescent studies. The emission spectrum of SDO show a strong emission band at 488 nanometer in DMSO water solution with excitation wavelength at 365 nanometer. The addition of DCP and DCNP to the SDO solution gradually increases the emission peak at 488 nanometer, leading to improvement in the emission intensity. The enhanced emission causes a visible color change from green to cyan under UV light, that is 365 nanometer. The emission changes reach saturation when approximately 30 equivalents of DCP and 20 equivalents of DCNP are added to the probe solution. To check the further selectivity of SDO, UV visible absorption studies were performed in presence of other guest analytes such as acetic acid, HCl, and etc. Results showed that only DCP and DCNP were detected by SDO, while other analytes did not exhibit any significant changes in the absorption spectral pattern. This indicates that SDO is highly selective for DCP and DCNP and can effectively differentiate them from other related analytes. Fabrication of test kit for selective detection of DCP and DCNP. The fabrication process involves dipping Wattman 40 filter paper in a DMSO solution of SDO and drying it under a hot air oven at 60 degrees Celsius. When different NARP agents, especially DCP and DCNP, are added to drop by drop to the dried paper and dried again, they cause the fluorescence to change from yellow to colorless and cyan under 365 nanometer UV lamp. This color change occurs because of the bond formation between probe SDO and DCP or DCNP, while other analytes do not participate in such bonding. Thus, the probe SDO can be used to detect G-series NARP agent in real samples under UV light. Deep stick method for selective detection of DCP and DCNP. Detecting DCP and DCNP in their solid and liquid form is easier, but it is more challenging in their vapor phase. To address this challenge, a simple deep stick method was introduced using Wattman filter paper soaked in the SDO solution and exposed to the vapors of DCP and DCNP. The filter paper changes from yellow to colorless in ambient light and showed a cyan fluorescence under UV light, indicating successful detection of DCP and DCNP vapors. Detection mechanism. The sensing mechanism of the chemodosimeter SDO with DCP and DCNP involves a chemical reaction between SDO and the NARP agent. When DCP and DCNP are added to the SDO, their electrophilic phosphonyl groups attract the nitrogen atom of the imine group in SDO, leading to the nucleophilic attack. This nucleophilic attack results in the formation of a new compound SDO DCP and SDO DCNP. At the same time, another compound called DHP is released, that is diethyl hydrogen phosphate. The formation of SDO DCP and SDO DCNP triggers an internal charge transfer process, that is ICT. This internal charge transfer process is responsible for observed ratiometric emission change and visible color change in SDO when exposed to DCP and DCNP. The emission intensity of the probe SDO at 488 nanometer is also enhanced due to the inflexibility of the compound SDO DCP and SDO DCNP formed after addition of DCP and DCNP to the SDO. Now we have come to the conclusion that our probe SDO can detect G-series NARP agent, DCP, DCNP in solid, liquid and gas phase respectively. We have created a SDO stain paper-based test kit for on-site detection and quantification of this NARP agent. Additionally, a deep stick experiment shows selective detection of DCP and DCNP vapors over the other NARP agents. Thank you very much. If you like this video, please subscribe to my YouTube channel.